Hello there, and welcome to the Dreamy Science Guy. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're the kind of person who likes drifting off to deep thoughts about the cosmos, rather than counting sheep. Either way, you're in the right place. Tonight, we're not just exploring the universe, we're asking something far more fundamental, something that sits at the very edge of what we can understand. We're asking why the universe has any rules at all. Take a moment to settle in. Let your shoulders relax, your breathing slow, your mind open to wonder. Because tonight's journey takes us to the foundation of everything. Not just what the laws are, but why they exist in the first place. Why does nature follow rules? Why does mathematics describe reality so precisely? Why is there something rather than nothing? These are questions that have kept philosophers awake for millennia, and physicists puzzled for centuries, and though we may not find all the answers, the journey itself is profound. Before we begin, if these calm explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin our journey into the deepest mystery of all. When we speak of the laws of nature, we're not talking about the kind of laws humans create, the rules written in legal books or posted on street signs. No one voted on the law of gravity. No parliament decreed that energy should be conserved. These laws are different, fundamentally so, and understanding what we mean when we call them laws is the first step in understanding why they exist at all. A law of nature in the scientific sense is a statement that describes a regular pattern in how the universe behaves. It's a description of what always happens everywhere, every time, without exception. When you drop a ball, it falls. When you heat water to 100 degrees Celsius at sea level, it boils. When you shine light through a prism, it separates into colours. These aren't coincidences or happy accidents. They're manifestations of underlying patterns, regularities that seem woven into the very fabric of reality itself. But here's where it gets interesting, where the wonder begins to seep in. These patterns aren't just local quirks of our planet or our solar system. They appear to be universal. The same force that makes an apple fall from a tree on Earth also keeps the moon in orbit around us and Earth in orbit around the sun. The same electromagnetic force that allows you to see these words also lights up distant stars and holds atoms together across the entire observable universe. The laws we discover here, in our tiny corner of space and time, seem to apply everywhere and everywhen. Consider what this means. The universe is unimaginably vast, stretching at least 93 billion light-years across in what we can observe and likely far, far beyond. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. It's existed for about 13.8 billion years. And throughout all of this immensity of space and time, the same rules apply. Hydrogen behaves the same way in a star 10 billion light-years away as it does in a laboratory here on Earth. Gravity weakens with the square of distance whether you're measuring it between two masses in your hand or between galaxies separated by cosmic voids. This universality is not something we should take for granted. It's deeply remarkable, even mysterious. Why should the rules be the same everywhere? Why shouldn't different regions of space have different laws, different forces, different constants? Why shouldn't the laws change over time, evolve or shift? And yet, as far as we can tell, they don't. From the moment of the Big Bang to the present day, from the smallest subatomic scale to the largest cosmic structures, the same fundamental patterns hold. Scientists describe these patterns using mathematics. They write equations, elegant strings of symbols that capture in precise language how things behave. Newton's law of universal gravitation, Einstein's field equations, Schrödinger's equation, Maxwell's equations. These mathematical statements don't just summarize what we've observed, they predict what we haven't yet seen. They tell us what must happen under conditions we've never tested, and when we finally do test them, when we perform the experiment or make the observation, nature confirms the prediction. Time and again, the equations prove reliable. But what exactly are these equations describing? Are they discovering something that was already there, some pre-existing structure written into reality? Or are they human inventions, useful fictions we've created to organize our experience? This question has puzzled thinkers for centuries. Plato believed that mathematical truths existed in a perfect realm beyond our material world, eternal and unchanging, and that our equations were imperfect glimpses of these ultimate forms. Others have argued that mathematics is simply a language we've invented, no more inherent to nature than English or Mandarin, just particularly useful for describing patterns. The physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. Writing in 1960, Wigner marvelled at how mathematical concepts developed for their own intrinsic interest, with no thought to practical application, often turned out to describe physical reality with shocking precision. Complex numbers, invented by mathematicians playing with algebraic puzzles, became essential to quantum mechanics. Group theory, an abstract mathematical framework, proved crucial for understanding fundamental particles. Differential geometry, developed to study curved surfaces, became the foundation of Einstein's general theory of relativity. How can this be? How can abstract mathematical ideas, created in the minds of mathematicians for purely aesthetic or logical reasons, turn out to be the very language in which the universe speaks? It's as if the cosmos was designed with mathematics as its grammar, its syntax, its vocabulary. Or perhaps it's that our minds, evolved to survive on the African savanna, somehow stumbled upon patterns of thought that align with the deep structure of reality. Either possibility is profound. Either possibility suggests something fundamental about the relationship between mind and matter, between thought and being. When we speak of natural laws, we're also making a claim about necessity. A law doesn't describe what sometimes happens or usually happens. It describes what must happen. It's not that objects occasionally fall when dropped. They always do. They have to, because the law of gravity is not a suggestion. This sense of necessity, of compulsion, is what makes laws different from mere patterns or regularities. The sun has risen every day for billions of years, but that's not a law, just a very long-running pattern based on laws of orbital mechanics and stellar physics. The law is deeper. It's about why the sun must continue rising as long as Earth continues rotating and orbiting. Yet even this raises puzzles. What makes a law necessary? Who or what enforces it? In human laws, there are lawmakers and enforcers, police and courts, but natural laws have no enforcement mechanism, no cosmic police checking that gravity is still pulling at the right strength, or that light is still travelling at the right speed. They simply are. Objects don't fall because someone is making them fall. They fall because that's what it means to exist in a universe with mass and space-time and the curvature that mass creates. The law emerges from the nature of reality itself. This brings us closer to the heart of our question. When we ask why the universe has laws, we're really asking several things at once. We're asking why there are regularities at all rather than pure chaos. We're asking why these particular laws rather than others. We're asking why the laws are mathematical in nature. We're asking why they're universal rather than local. And lurking beneath all of these questions is perhaps the deepest one of all. Why is there something rather than nothing? Because any answer to why there are laws must ultimately confront the question of why there is anything for laws to govern. The ancient Greeks were among the first to systematically ask these questions. Thales of Miletus, often called the first philosopher, looked at the world and asked not what the gods had ordained, but what natural principles might explain what he saw. His student Anaximander proposed that the universe arose from an undefined, boundless source, something he called the apeiron. Another student, Anaximenes, suggested air was the fundamental substance from which all else emerged through processes of condensation and rarefaction. These thinkers were groping toward the idea that nature operates according to principles, that there are reasons things happen the way they do. Later, Plato would propose his theory of forms, perfect ideals existing in a realm beyond our material world, with the physical universe being an imperfect copy of these eternal templates. Aristotle would develop a more empirical approach, studying the world directly and proposing 4 types of causes: material, formal, efficient, and final. Each of these ancient frameworks was an attempt to understand why the world behaves in regular, predictable ways. Why do things fall? Why do plants grow? Why do the stars move across the sky in their eternal dance? But it wasn't until the scientific revolution of the 16th and 17th centuries that humans truly began to crack the code. Galileo, Newton, Kepler, Descartes. These thinkers developed a new method for understanding nature. They observed carefully, measured, precisely, and then sought mathematical relationships that could predict future observations. They discovered that nature could be interrogated, that experiments could reveal her secrets, that mathematics was her language, and in doing so, They began to uncover the laws that would reshape our understanding of the universe. Yet even as we've uncovered more and more laws, even as our equations have grown more sophisticated and our predictions more accurate, the fundamental mystery remains. Why are there laws at all? Why does the universe play by rules? Why is it comprehensible to minds like ours? These questions haven't gone away with scientific progress. If anything, they've become more acute, more pressing, more profound. Because the more we learn about how the universe works, the more we're forced to confront the question of why it works at all. The historical journey, how humans discovered universal laws. The story of how humans came to understand that the universe operates according to laws is one of the great intellectual adventures of our species. It's a tale spanning millennia, crossing continents, involving countless minds, each adding their piece to a puzzle that still isn't complete. And it begins, as many great stories do, with simply looking up. Ancient peoples everywhere noticed patterns in the sky. The sun rose and set with reliable regularity. The moon waxed and waned in its 29.5-day cycle. Certain bright points of light, which they called wanderers or planets, moved against the background of fixed stars in curious looping paths. The Babylonians, the Egyptians, the Chinese, the Maya all developed sophisticated methods for tracking these celestial movements. They created calendars, predicted eclipses, and mapped the heavens with remarkable precision. But knowing that something happens and knowing why it happens are very different things. The Babylonians could predict lunar eclipses centuries in advance using their mathematical tables, yet they likely attributed these events to the actions of gods or demons. The pattern was clear, but the underlying cause remained hidden behind a veil of mythology and religious explanation. It would take a fundamental shift in human thinking to move from tracking patterns to understanding principles. That shift began in ancient Greece. The pre-Socratic philosophers made a revolutionary proposal. Maybe natural phenomena have natural causes. Maybe we don't need gods to explain why the sun shines or why lightning strikes. Maybe there are underlying principles, logos, rational patterns that govern how things behave. Pythagoras and his followers went further, proposing that numbers and mathematical relationships were the key to understanding reality. They discovered that musical harmony arose from simple ratios, that geometric patterns appeared throughout nature, that mathematics seemed to be nature's secret language. Plato took this mathematical mysticism and gave it philosophical depth. In his theory of forms, the perfect mathematical circle exists in an eternal realm of pure ideas, while the circles we draw on paper or trace in sand are mere imperfect copies. The true reality isn't found in the changing, chaotic physical world, but in the unchanging realm of perfect mathematical forms. This view would influence Western thought for thousands of years, creating a tension that still exists today between those who see mathematics as discovered and those who see it as invented. Aristotle, Plato's student, took a different approach. He was more interested in the physical world itself, in studying animals and plants, in understanding motion and change. Aristotle proposed that every object has a natural place and a natural motion toward that place. Rocks fall because Earth naturally moves toward the center of the cosmos. Fire rises because that's its natural tendency. He developed elaborate systems for categorizing causes and understanding change, and, while many of his specific ideas would later prove wrong, his method of careful observation and systematic classification laid groundwork for future science. But the ancient Greeks, for all their brilliance, lacked a crucial ingredient: the systematic use of experimentation. They preferred thought experiments to actual experiments, logical deduction to empirical testing. It wasn't until the Islamic Golden Age, from the 8th to the 14th centuries, that scholars began to emphasize experimental verification of theories. Al-Hazen, also known as Ibn al-Haytham, wrote extensively about optics and the scientific method, arguing that theories must be tested against observation. Al-Biruni performed careful measurements to determine the Earth's radius. These scholars preserved and extended Greek knowledge, while adding their own crucial innovations. The real revolution began in Europe during the 16th and 17th centuries. Nicholas Copernicus, though working with essentially the same observational data available to ancient astronomers, made a radical proposal. What if Earth isn't the center of everything? What if we orbit the sun rather than the sun orbiting us? His heliocentric model didn't immediately explain everything better than the geocentric model, but it planted a seed. It suggested that the universe might not be organized the way it appears from our limited vantage point. Johannes Kepler, working with the meticulous observations of Tycho Brahe, discovered that planets don't move in perfect circles but in ellipses, with the sun at one focus. This was a shock. For 2,000 years since Plato, thinkers had assumed celestial motions must be circular, the perfect form. But nature didn't care about Platonic ideals. The orbits were elliptical, and Kepler found precise mathematical laws describing their motion. Planets sweep out equal areas in equal times, and the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These were real, testable, mathematical laws governing celestial mechanics. Meanwhile, Galileo Galilei was revolutionizing how we study motion on Earth. He rolled balls down inclined planes and timed their descent. He dropped objects from towers, he swung pendulums and measured their periods, and crucially, he wrote down his results in mathematical language. He discovered that objects accelerate uniformly when falling, that their speed increases by the same amount each second regardless of their weight. This contradicted Aristotle's claim that heavier objects fall faster. Galileo showed that careful measurement and mathematical analysis could reveal truths about nature that pure reasoning might miss. But it was Isaac Newton who tied everything together. In his Philosophia Naturalis Principia Mathematica, published in 1687, Newton showed that the same force that makes apples fall from trees keeps the moon in orbit and the planets circling the sun. He unified celestial and terrestrial physics under one mathematical framework. His law of universal gravitation stated that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. One simple equation explained everything from falling objects to planetary orbits to the tides. Newton's achievement can hardly be overstated. He didn't just discover a law of nature. He showed that laws of nature exist in a form we can write down, test, and use to make predictions. He demonstrated that the universe is governed by mathematical principles that our minds can grasp. His work established the paradigm that would guide physics for the next 200 years. Observe nature, find the mathematical patterns, express them as laws, and use those laws to predict new phenomena. The 18th and 19th centuries saw an explosion of new discoveries. Benjamin Franklin and others explored electricity and magnetism, revealing strange new forces that could attract or repel without contact. Michael Faraday, largely self-taught, performed beautiful experiments showing that electricity and magnetism were intimately related, that moving magnets could generate electric currents, and electric currents could create magnetic fields. Then James Clerk Maxwell took Faraday's experimental insights and expressed them in 4 elegant equations that unified electricity, magnetism, and even light into a single electromagnetic theory. Maxwell's equations predicted that electromagnetic waves should travel at a certain speed, and that speed turned out to be exactly the speed of light. Light itself was revealed to be an electromagnetic phenomenon. Thermodynamics emerged as scientists studied heat engines and the conversion of heat into work. The laws of thermodynamics, that energy is conserved, that entropy always increases in closed systems, became pillars of physics as fundamental as Newton's laws. These weren't just abstract principles, but practical truths with real consequences, explaining everything from why perpetual motion machines are impossible to the ultimate fate of the universe. Meanwhile, chemistry was being transformed by the realization that matter is made of atoms obeying definite rules of combination. Dmitri Mendeleev organized the elements into his periodic table, revealing that chemical properties repeat in predictable patterns based on atomic weights. This periodicity itself demanded explanation, hinting at some deeper structure to atoms. That deeper structure would be revealed in the 20th century with the development of quantum mechanics. Max Planck, trying to explain blackbody radiation, proposed that energy comes in discrete chunks or quanta. Einstein extended this idea, proposing that light itself consists of particles called photons. Niels Bohr applied quantum ideas to atoms, explaining why they emit and absorb light at specific frequencies. Then Heisenberg, Schrödinger, Dirac, and others developed the full mathematical framework of quantum theory, discovering that at the smallest scales, nature is fundamentally probabilistic, that particles exist in superpositions of states, that observation affects what is observed. Around the same time, Einstein was revolutionizing our understanding of space, time, and gravity. His special theory of relativity showed that space and time are not absolute but relative, intertwined into a single space-time continuum. Different observers moving at different speeds would disagree about measurements of distance and duration, yet they would all agree on the laws of physics. Then his general theory of relativity revealed that gravity is not a force in the Newtonian sense, but a curvature of space-time itself. Mass bends space-time, and objects follow the straightest possible path through this curved geometry. The Sun doesn't pull on Earth. Rather, Earth follows a curved trajectory, through the space-time that the Sun's mass has warped. The 20th century also saw the discovery of new forces and particles. Ernest Rutherford's experiments revealed that atoms have tiny, dense nuclei. Marie Curie's work on radioactivity showed that atomic nuclei can transform, releasing energy and particles. The strong nuclear force was discovered, the powerful but short-range force that holds atomic nuclei together, despite the electromagnetic repulsion between positively charged protons. The weak nuclear force was found, responsible for certain types of radioactive decay. By the 1970s, physicists had assembled what's called the Standard Model of Particle Physics, a comprehensive theory describing all known particles and three of the four fundamental forces: electromagnetism, the strong force, and the weak force. The Standard Model makes incredibly precise predictions that have been confirmed by countless experiments. It predicted the existence of particles like the W, and Z bosons and the top quark years before they were discovered. In 2012, it was confirmed with the discovery of the Higgs boson, the last piece of the puzzle that explains how particles acquire mass. Yet for all this progress, major mysteries remain. The Standard Model doesn't include gravity. We still lack a quantum theory of gravitation that would fully unify our understanding. We don't know what dark matter is, the invisible substance that makes up about 85% of the matter in the universe. We don't know what dark energy is, the mysterious force causing the universe's expansion to accelerate. We don't know why there's more matter than antimatter, when the laws of physics seem to treat them symmetrically. We don't know why the fundamental constants have the values they do, and lurking beneath all these specific mysteries is the deepest one. Why are there laws at all? The history of science is a history of discovering and refining these laws, of finding ever more precise and comprehensive mathematical descriptions of nature's behavior. But discovering what the laws are doesn't explain why they exist. That question remains as profound and puzzling today as it was when the first philosophers looked at the sky and wondered why the stars move in their courses, the four fundamental forces, nature's basic rules. At the heart of our universe's lawfulness are four fundamental forces, four basic interactions that govern how particles behave, how atoms form, how stars shine, how galaxies spin through space. Everything that happens in the physical universe can be traced back to these four forces, acting according to their specific rules. Understanding these forces is understanding the grammar of nature, the basic vocabulary with which the cosmos writes its story. The force you're most familiar with is gravity. It's what keeps your feet on the ground, what makes dropped objects fall, what prevents you from floating off into space. Gravity is the universal attraction between all objects with mass. Every particle of matter in the universe attracts every other particle. The Earth pulls on you, and you pull back on Earth. The strength of this pull depends on mass and distance. More massive objects create stronger gravitational fields, and the force weakens as objects move farther apart, specifically decreasing with the square of the distance. Isaac Newton described gravity mathematically in 1687, but Albert Einstein showed in 1915 that Newton's picture was incomplete. In Einstein's general relativity, gravity isn't really a force in the traditional sense. Instead, mass and energy curve space-time, and objects simply follow the straightest possible path through this curved geometry. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it will curve toward the bowling ball not because the ball's pulling on it, but because the sheet itself is curved. Gravity works similarly, though in 3 spatial dimensions plus time rather than 2 dimensions. Gravity has some unique properties among the forces. It's always attractive, never repulsive. Unlike electromagnetic forces that can push as well as pull, gravity only pulls. It works across infinite distances, though it gets weaker with separation. And it's astoundingly weak. You might not think of gravity as weak when you're struggling to climb stairs, but consider this. The entire mass of planet Earth pulling down on a paper clip can be overcome by a small refrigerator magnet. The electromagnetic force generated by that tiny magnet overpowers the gravitational force of an entire planet. If gravity isn't weak, magnetism must be incredibly strong. Yet gravity's weakness is paired with its ubiquity. Because it affects everything with mass or energy, and because it always attracts, gravity accumulates. Individual atoms barely pull on each other, but collect enough atoms together, and their combined gravitational pull becomes significant. Gather enough mass in one place, and gravity can crush matter into exotic states. White dwarfs, where electrons are squeezed as tightly as quantum mechanics allows, neutron stars where atomic nuclei merge into continuous nuclear matter, black holes where space-time curves so severely that not even light can escape. On cosmic scales, gravity is the dominant force, the architect of large-scale structure. It pulls gas clouds together to form stars. It binds stars into galaxies and galaxies into clusters and clusters into superclusters. It determines the ultimate fate of the universe, whether it will expand forever or eventually collapse back in a big crunch. For all its weakness at small scales, gravity is the force that shapes the cosmos. The electromagnetic force is in many ways more familiar than gravity, though you might not recognize it. Every time you see anything, you're experiencing electromagnetism. Light is an electromagnetic wave. Every time you touch something, you're feeling electromagnetic repulsion between the electrons in your fingertips and the electrons in whatever you're touching. Chemistry is almost entirely electromagnetic. Chemical bonds form because of electromagnetic attractions between electrons and nuclei. Your body holds together because of electromagnetic forces. Like gravity, electromagnetism can work over infinite distances, but unlike gravity, it can both attract and repel. The rule is simple. Opposite charges attract like charges repel. Electrons, which carry negative charge, repel other electrons but attract protons, which carry positive charge. This ability to both push and pull makes electromagnetism far more varied and interesting than gravity. Where gravity can only bring things together, electromagnetism can create structures, patterns, arrangements based on the interplay of attraction and repulsion. James Clerk Maxwell unified our understanding of electricity and magnetism in the 1860s, showing that there are really two aspects of a single electromagnetic force. A changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. This back and forth can propagate through space as an electromagnetic wave, traveling at the speed of light. Light, radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, gamma rays, all of these are electromagnetic waves, differing only in frequency and wavelength. Quantum mechanics revealed that at the smaller scales, the electromagnetic force is mediated by particles called photons. When an electron and a proton interact electromagnetically, in the quantum picture they exchange virtual photons. These aren't photons you could detect directly, but they're real enough to carry the force between the charged particles. This quantum picture of forces, where interactions happen through the exchange of force-carrying particles, applies to all the fundamental forces except gravity, which we haven't yet managed to incorporate into quantum theory. Electromagnetism is vastly stronger than gravity. The electromagnetic force between two protons is about 10 to the 36 times stronger than the gravitational force between them. That's a 10 followed by 36 zeros. This enormous difference in strength is part of what makes our universe interesting. Gravity is strong enough to hold planets together, but weak enough that electromagnetic forces can easily move individual atoms around. If gravity were much stronger relative to electromagnetism, interesting chemistry would be impossible. If it were much weaker, stars and planets might never form. The strong nuclear force is perhaps less intuitive because we don't experience it directly in daily life. It operates only at extraordinarily short ranges, about 100 trillion times smaller than the thickness of a human hair. But at these tiny distances inside atomic nuclei, the strong force is indeed strong, about 100 times stronger than her electromagnetism. The strong force is what holds atomic nuclei together. Protons, all positively charged, should repel each other electromagnetically. The nucleus of a carbon atom contains 6 protons crammed incredibly close together. Why don't they fly apart? The strong force binds them together. It's powerful enough at nuclear distances to overcome the electromagnetic repulsion and glue protons and neutrons into stable configurations. The strong force is mediated by particles called gluons, and it binds together the quarks that make up protons and neutrons. Quarks come in 6 types, or flavors: up, down, strange, charm, top, and bottom. Protons consist of 2 up quarks and 1 down quark. Neutrons consist of 2 down quarks and 1 up quark. The quarks are held together so tightly by the strong force, exchanging gluons, that we never see individual quarks in isolation. Try to pull quarks apart and the force actually gets stronger rather than weaker, like trying to stretch an incredibly stiff spring. Put enough energy in, and instead of separating the quarks, you create new quark-antiquark pairs. The strong force is uniquely confining. This force is responsible for nuclear energy. When nuclei split in fission or fuse in fusion, the strong force is being rearranged, and the energy released comes from the difference in binding energy. The sun shines because hydrogen nuclei fuse into helium in its core, releasing energy that eventually reaches us as light and heat. Nuclear weapons derive their devastating power from rapidly releasing energy stored in strong force bonds. The strong force is why there's energy in atomic nuclei at all. The weak nuclear force is perhaps the most mysterious of the 4. Like the strong force, it operates only at very short ranges, even shorter, about 1,000th the range of the strong force, and despite its name, it's actually stronger than gravity, just weaker than the other forces. The weak force is responsible for certain types of radioactive decay, specifically beta decay, where neutrons transform into protons or vice versa. In beta decay, a neutron in an atomic nucleus transforms into a proton, releasing an electron and an antineutrino, or a proton can transform into a neutron, releasing a positron and a neutrino. These transformations change one element into another. When carbon-14 decays, it becomes nitrogen-14. The weak force makes this possible by allowing one type of quark to change into another type. Inside a neutron, one of the down quarks can transform into an up quark via the weak force, converting the neutron into a proton. The weak force is also crucial to how stars work. The sun doesn't just fuse hydrogen into helium through the strong force alone. The process requires weak force interactions to convert protons into neutrons, allowing the right nuclear configurations to form. Without the weak force, stellar, fusion would be impossible, stars would never ignite, and the universe would be a far colder and darker place. In the 1960s and 70s, physicists discovered that the electromagnetic and weak forces are actually 2 aspects of a single electroweak force. At high enough energies, temperatures that existed in the early universe shortly after the Big Bang, these forces are unified, indistinguishable. As the universe cooled and expanded, this symmetry broke, and the electroweak force split into the distinct electromagnetic and weak forces we observe today. This unification, for which Sheldon Glashow, Abdus Salam, and Steven Weinberg won the Nobel Prize, suggests that nature's fundamental laws may be simpler and more unified than they first appear. These 4 forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern every interaction in the physical universe. When you turn on a light, electromagnetism is at work. When you fall, gravity is acting. When the sun shines, it's fusion powered by the strong and weak forces. When particles decay in radioactive materials, the weak force is responsible. Everything that happens because these forces act according to their mathematical laws. But why these 4 forces? Why not 3 or 5 or 17? Why these particular strengths, these specific ranges, these exact rules? And at the most fundamental level, why should there be forces at all? What makes particles interact rather than simply existing in isolation? These questions bring us closer to the heart of the mystery. Physicists dream of a theory of everything, a single unified framework that would show all 4 forces as different aspects of one ultimate force. They've had some success. The electroweak unification showed that 2 forces are really one at high energies. Grand unified theories aim to bring the strong force into this picture, showing that at even higher energies the strong, weak, and electromagnetic forces unify. String theory and other approaches try to include gravity in this ultimate unification. But even if we achieve a theory of everything, even if we reduce all forces to manifestations of a single underlying principle, the question remains, why that principle? Why those equations rather than others? The journey to understand the forces has been remarkably successful at describing what happens and how it happens. But it has barely scratched the surface of why it happens at all. The forces exist, they follow rules, they govern the cosmos, but their existence remains, at its core, an unexplained fact, a brute feature of reality that we've learned to describe but not to explain. The constants, numbers that define reality. If the fundamental forces are the grammar of the universe, the fundamental constants are its vocabulary. These are special numbers that appear in the equations of physics, numbers that don't change across space or time, numbers that define the basic properties of reality itself. And remarkably, the values of these constants seem finely tuned to allow for the existence of complex structures, including stars, planets, and life. Perhaps the most famous constant is the speed of light, denoted c in equations. In a vacuum, light always travels at exactly 299,792,458 meters per second. This isn't just the speed at which light happens to move, it's the maximum speed limit of the universe, the speed at which all massless particles travel, the speed at which information and causality propagate. Special relativity showed that the speed of light is the same for all observers regardless of their motion. If you're standing still and measure the speed of a passing light beam, you get c. If you're on a spaceship travelling at 99% the speed of light and measure a passing light beam, you still get c. This constancy of light speed, seemingly bizarre, is what led Einstein to realise that space and time must be relative, malleable, intertwined. But why does light travel at this particular speed? The value of c emerges from two other fundamental constants: the permittivity and permeability of free space, which govern how electromagnetic fields behave. The speed of light is the speed at which electromagnetic waves propagate through the vacuum, determined by these underlying properties of space-time. But this just pushes the question back. Why do those constants have the values they do? The gravitational constant g sets the strength of gravity. It appears in Newton's law of gravitation and in Einstein's field equations. Its value is about 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared. That might seem like a random collection of numbers and units, but this single value determines how strongly masses attract each other, how big planets and stars need to be to hold together, how fast the universe expands. Change g by even a small amount and the universe would be dramatically different. Planck's constant, h, sets the scale of quantum effects. It relates a particle's energy to its frequency, and it determines the fundamental graininess of reality. The fact that energy comes in discrete chunks rather than being infinitely divisible. Planck's constant is tiny, about 6.6 times 10 to the negative 34 joule seconds, which is why we don't notice quantum weirdness in our everyday lives. But at atomic and subatomic scales, this constant is crucial. It sets the size of atoms, determines the properties of chemical bonds, governs the uncertainty principle that makes certain pairs of measurements incompatible. The charge of an electron, E, is another fundamental constant. Every electron in the universe has exactly the same electric charge, about negative 1.6 times 10 to the negative 19 coulombs. This charge determines how strongly electrons interact electromagnetically with protons and with each other. It sets the strength of chemical bonds, determines how easily electric currents flow, governs the behavior of atoms and molecules. But physicists often talk about something called the fine structure constant, which is a dimensionless combination of the electron charge, the speed of light, and other constants. Its value is about 1 divided by 137. This number characterizes the strength of electromagnetic interactions and appears throughout quantum electrodynamics. Interestingly, it's purely a number, not dependent on what units you choose to measure things in. Whether you use meters or light years, kilograms or solar masses, the fine structure constant is always approximately 1 over 137. And yet we have no idea why it has this value. It's not derived from any deeper theory. It's just measured, determined by experiment. The masses of fundamental particles are also constants whose values we don't understand. The electron has a particular mass, about 9.1 times 10 to the negative 31 kilograms. The up quark has its mass, the down quark has a different mass, the top quark has yet another mass nearly 200,000 times heavier than the electron. We can measure these masses with great precision, but we can't predict them from any deeper principle. They're inputs to our theories, numbers we have to plug in, not outputs that emerge from the mathematics. The cosmological constant, usually denoted by the Greek letter lambda, represents the energy density of empty space. Einstein introduced it into his equations of general relativity, initially as a way to create a static universe, then abandoned it when Edwin Hubble discovered the universe is expanding. But in the late 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating. Something is pushing space apart, working against gravity's tendency to pull things together. We call this mysterious something dark energy, and the simplest explanation is that it's a cosmological constant, a kind of energy inherent in space itself. The cosmological constant's measured value is tiny but not zero, about 10 to the negative 52 per meter squared in natural units. This leads to one of the most perplexing problems in physics. When we try to calculate what the cosmological constant should be based on quantum field theory, we get an answer that's wrong by a factor of 10 to the 120, 1 followed by 120 zeros. This has been called the worst prediction in the history of physics. The theoretical expectation is fantastically different from what we actually observe. We have no idea why the cosmological constant is so small, yet if it were much larger, the universe would have expanded so rapidly that galaxies could never form. This brings us to the deep puzzle of fine-tuning. Many of the fundamental constants seem precisely calibrated to allow for the existence of complex structures like atoms, stars, planets, and ultimately life. Change them by even modest amounts, and the universe becomes sterile, unable to produce the rich variety of structures we observe. Consider the strong nuclear force. If it were just a few percent stronger, protons and neutrons would bind together too readily, and almost all the hydrogen in the early universe would have fused into heavier elements. Stars, which run on fusing hydrogen, would quickly run out of fuel. If the strong force were a few percent weaker, deuterium, a heavy isotope of hydrogen that's crucial for stellar fusion, wouldn't form. Stars might never ignite at all. The electromagnetic force is similarly constrained. If it were significantly stronger, chemical bonds would be so tight that molecules couldn't easily rearrange, making chemistry sluggish and perhaps preventing the complex molecular interactions life requires. If it were significantly weaker, atoms would be huge and loosely bound, and it's unclear if complex chemistry could exist at all. The ratio between the electromagnetic and gravitational forces is particularly critical. Gravity, as we mentioned, is about 10 to the 36 times weaker than electromagnetism. This huge disparity allows for interesting structure at multiple scales. Electromagnetic forces can arrange atoms into complex molecules without gravity interfering, but gravity can gather huge numbers of atoms into planets and stars. If this ratio were substantially different, either stars would be impossibly small or planets impossibly large. The masses of particles also seem fine-tuned. If the electron were much heavier, atoms would be tiny and chemical bonds very different. If quarks had different mass ratios, the proton and neutron masses would be altered, potentially making nuclei unstable or preventing them from forming. If the Higgs field had a different strength, giving particles different masses, the whole landscape of physics would transform. Even the number of spatial dimensions seems significant. Our universe has 3 spatial dimensions. String theory suggests there might be more, but curled up so small we don't notice them. But why 3 large dimensions? In 2 spatial dimensions, certain types of wave equations that govern forces couldn't work properly. In 4 or more spatial dimensions, planetary orbits would be unstable. There would be no stable pattern of planets circling stars. 3 dimensions seem like a kind of sweet spot. Some physicists have tried to calculate how much variation the constants could tolerate, while still allowing for life, or at least for structures like stars and atoms. The results are striking. In many cases, the allowed range is surprisingly narrow. Change things by a factor of 2 or 3, sometimes even less, and you get a universe that seems fundamentally inhospitable to complexity. Martin Rees, the British cosmologist, argued that 6 numbers are particularly crucial for determining the character of our universe. There's n, the ratio of electromagnetic to gravitational forces, roughly 10 to the 36. There's epsilon, the efficiency of nuclear fusion, about 0.007. There's omega, which relates to the cosmic density and determines whether the universe will recollapse or expand forever. There's lambda, the cosmological constant. There's Q, measuring how tightly bound galaxy clusters are. And there's D, the number of spatial dimensions, which is 3. Rees contended that changing any of these significantly would result in a very different cosmos. Of course, one might ask whether our intuitions about what makes a universe interesting or life-permitting are too narrow. Perhaps we're suffering from a failure of imagination, unable to conceive of entirely different forms of complexity or life that might exist under very different laws and constants. This is the carbon chauvinism critique. Maybe we're too focused on carbon-based life chemistry because it's the only kind we know. Perhaps silicon-based life, or plasma-based life, or quantum computer-like structures could exist under different conditions, and we'd find those universes equally rich and interesting if we could experience them. But even granting that possibility, the degree of apparent fine-tuning is remarkable enough to demand explanation. It's not just that one or two constants seem fortuitously chosen, it's that many of them, governing different aspects of physics, all fall within ranges that allow for the universe we observe, and changing any of them substantially would drastically alter reality. This fine-tuning has led to intense debate. Some see it as evidence for a creator, a designing intelligence that chose the constants to allow for life. Others invoke the anthropic principle, arguing that we inevitably observe a universe with constants compatible with our existence. We couldn't observe any other kind. Still others propose a multiverse, suggesting there are countless universes with different constants, and we naturally find ourselves in one where the constants allow for observers. But beneath these debates lies a simpler mystery. Why do constants exist at all? Why should there be certain numbers that appear in fundamental equations, numbers that don't change, numbers that seem built into the structure of reality? Why isn't the strength of gravity something that fluctuates or varies from place to place? Why are these values stable across billions of light years and billions of years? The constants, in a sense, are the universe's personality, the specific details that make it what it is rather than something else. The laws tell us what form nature's behavior takes, but the constants fill in the quantitative details. And just as the existence of laws is mysterious, so too is the existence of these special numbers that define realities, parameters. They're part of what makes the universe comprehensible and consistent, but their origins remain deeply puzzling. The fine-tuning mystery. Why these laws and not others? The observation that our universe's fundamental constants appear fine-tuned for complexity, and life leads naturally to one of the most profound questions in cosmology and philosophy. Why does the universe have these particular laws and constants rather than others? This question goes beyond merely asking what the laws are or even how they came to be. It asks why these specific laws exist at all, why this particular configuration of reality rather than some other or none. The fine-tuning observation can be stated precisely. If you imagine randomly varying the fundamental constants and laws, the vast majority of possible universes would be radically different from ours, typically far simpler and unable to support complex structures. Change the strength of gravity slightly, and stars either burn out almost, instantly or never ignite at all. Adjust the strong nuclear force a bit, and atomic nuclei become unstable or impossible to form. Modify the mass of the electron even modestly, and chemistry as we know it disappears. Our universe seems to sit at a special point in the space of all possible universes, a point where richness and complexity are possible. This apparent specialness demands explanation. One possibility is simply to accept it as a brute fact, an inexplicable feature of reality that we just have to live with. Philosopher Bertrand Russell took this position when he said, "I should say that the universe is just there, and that's all." From this perspective, asking why the universe has its particular laws is meaningless or misguided. The laws simply are what they are, and no deeper explanation is possible or necessary. The universe doesn't need a reason to exist any more than the number pi needs a reason to have its particular value. This position has some philosophical appeal. After all, any explanation has to stop somewhere. If you explain the laws by appealing to some deeper principle, you can then ask why that principle holds. If you explain that principle with something even deeper, the regress continues. Eventually, you seem forced to accept something as simply given, unexplained, a foundation upon which everything else rests. So why not stop at the laws themselves? Why not treat them as the ground floor of explanation? The problem is that this feels unsatisfying when we're confronted with fine-tuning. If there's only one way the universe could be, one set of laws that necessarily exists, then fine-tuning isn't so surprising. But if the laws could have been different, if other values for the constants were possible, then it seems remarkably fortunate that we ended up with ones permitting complexity. As an analogy, imagine finding a knob with infinitely many settings, where only one tiny range of settings allows for anything interesting to happen, and discovering the knob is set precisely in that narrow range. You'd want to know why. Saying it just is feels inadequate. Another response is to invoke God or some other designing intelligence. This was the explanation favoured by many thinkers historically, and still advocated by some today. The universe is fine-tuned because it was designed to be that way. An intelligent creator chose the laws and constants deliberately, perhaps specifically to allow for life and consciousness. This moves the mystery. We no longer need to explain the law's fine-tuning, but we do need to explain the existence and nature of the designer. Why does this God exist? Why did this God choose these particular laws? But for some, this is progress. Better to explain the universe's properties by reference to an intentional agent than to accept them as inexplicable coincidence. The modern version of this argument, sometimes called the teleological argument or argument from design, says that the fine-tuning is evidence for a designer in the same way that finding a watch on a beach is evidence for a watchmaker. Complex, purposeful arrangements don't arise by chance. They require intelligent planning. The universe's laws and constants are complex and purposeful in that they permit complex structures, including life. Therefore, they likely result from intelligent design. Critics raise several objections. First, attributing the universe's properties to a designer doesn't truly explain them. It just passes the mystery on to the designer. Second, we have extensive experience with human designers and can recognize their work because we understand their goals and methods. But we have no experience with cosmic designers, so it's unclear what criteria we should use to identify their handiwork. Third, the argument assumes that a simple, barren universe would be somehow more natural or expected than a complex one. But this assumption itself needs justification. Why should simplicity be the default? A third response is to invoke the anthropic principle, though this comes in several versions with different implications. The weak anthropic principle simply observes that any observation we make must be compatible with our existence as observers. We shouldn't be surprised to find ourselves in a universe with laws permitting complex structures and life, because we couldn't exist in a universe without such laws. This doesn't explain why the universe is life-permitting. It just points out that our observation of life-permitting laws is subject to selection bias. We can only observe universes we can exist in. The weak anthropic principle is tautological but not entirely trivial. It reminds us to be careful about inferring design or coincidence from observations that are selection-affected. If you survey people leaving a casino and find that an implausibly large fraction report winning money, you shouldn't conclude the casino is giving away free money. You should realize that people who lose are less likely to talk to you, so your sample is biased. Similarly, we're observing the universe from the biased perspective of life forms that need certain conditions to exist. The strong anthropic principle goes further, suggesting that the universe must have properties allowing life to develop at some stage. This is more controversial because it seems to imply some kind of necessity or purpose to our existence. Why must the universe produce observers? Who or what requires this? The strong anthropic principle shades into teleological thinking, suggesting the universe has a goal or function that includes producing conscious observers. Both versions of the anthropic principle become more powerful if combined with a multiverse hypothesis. If there exist many universes with different laws and constants, then the weak anthropic principle provides a potential explanation for fine-tuning. The vast majority of universes might be sterile and simple, but we necessarily find ourselves in one of the rare ones that permits complexity and life. The observation of fine-tuning is then no more surprising than a lottery winner, being surprised they won. Someone had to win, and naturally it was someone who exists to express surprise. The multiverse idea comes in various forms. In eternal inflation models, which we'll explore more later, quantum fluctuations during an inflationary epoch cause some regions of space to stop inflating and become distinct universes, while other regions continue inflating, potentially forever. Each bubble universe might have different low-energy physics, different effective laws and constants, determined by how certain fields settled into their lowest energy states. We live in one bubble with particular properties, but there are countless others with different properties. String theory provides another route to a multiverse through what's called the landscape. String theory, a candidate for a theory of everything, suggests that the fundamental entities aren't particles but tiny vibrating strings, and the different vibration modes correspond to different particles. The mathematics allows for many possible configurations of extra dimensions and field values, perhaps 10 to the 500 distinct possibilities. Each corresponds to a different low-energy physics, a different set of effective laws and constants. If all these possibilities are realized somewhere in an eternal inflation multiverse, we get an enormous landscape of possibilities, and again, we observe one that allows for observers. The multiverse offers an elegant solution to fine-tuning. There's no need for design or inexplicable coincidence, because all possibilities are realized somewhere. But it raises problems of its own. First, it's not clear that multiverse theories are testable. If the other universes are causally disconnected from ours, if we can never observe or interact with them even in principle, then are they truly part of physics or just metaphysical speculation? Some physicists argue that a theory predicting a multiverse can still be tested through its other predictions and through its ability to explain things like fine-tuning without adding arbitrary parameters. Others insist that any legitimate scientific theory must make specific predictions that can be empirically confirmed or refuted, and multiverse theories fail this test. Second, the multiverse leads to probability puzzles. If there are infinitely many universes with all possible properties, then everything that can happen does happen infinitely many times. In such a setting, how do you calculate probabilities? How do you explain why we observe particular values for constants rather than other possible values? Various anthropic reasoning principles have been proposed to deal with this, like the self-sampling assumption, which says you should reason as if you were a random observer from among all possible observers, but these principles are controversial and lead to paradoxes. Third, one might question whether the multiverse really solves the fine-tuning problem or just moves it. The multiverse hypothesis requires its own laws, the laws of eternal inflation, the laws of string theory, whatever generates the multiple universes. Why do these meta-laws exist? Why do they produce a multiverse rather than just one universe? You've explained why our particular universe has its particular constants, but you haven't explained why there's a multiverse-generating mechanism rather than nothing at all. The mystery has been pushed back but not eliminated. A different approach suggests that the appearance of fine-tuning might be an illusion arising from our ignorance. Perhaps the fundamental constants aren't independent quantities that could have had different values. Perhaps they're all determined by some deeper principle we haven't discovered yet, a theory of everything that would show these are the only possible values consistent with mathematical coherence. In that case, there's no fine-tuning to explain because there's no space of alternative possibilities. The universe couldn't have been any different. This idea draws inspiration from mathematics. Why does pi equal approximately 3.14159? Not because someone chose it or because we're in one mathematical universe among many. It equals what it does because of what circles are, because of the logical structure of geometry. Perhaps the laws of physics are similarly determined, not arbitrary facts that need explanation, but necessary truths that follow from some deep logical or mathematical principle. But even if the laws are uniquely determined, that would still leave the question of why those particular mathematical structures are instantiated in physical reality. Why does the universe follow these specific mathematical patterns rather than others, or none? You'd still need to explain why mathematics applies to reality, why there are physical laws at all, not just why they take a particular form. Some thinkers have proposed that all possible mathematical structures exist as physical realities, the mathematical universe hypothesis. According to this view, every consistent mathematical structure corresponds to some universe, and we inhabit the one corresponding to our particular mathematical structure. This dissolves the question of why our laws exist. They exist because they're mathematically possible, and everything mathematically possible exists. But this raises all the problems of multiverse theories, plus additional puzzles about what it means for mathematical structures to exist, and why we should believe in such an extravagant ontology. Yet another approach emphasizes the role of symmetries. Many fundamental laws embody symmetries: invariance under translations in space and time, rotations, Lorentz transformations, gauge symmetries. These symmetries are deeply connected to conservation laws through Noether's theorem. Perhaps requiring certain natural symmetries constrains the laws to something close to what we observe. This is a working principle in theoretical physics. Start with symmetries and see what laws must follow. But symmetries don't fully determine everything. The values of coupling constants, mass ratios, mixing angles, these are parameters that can vary while preserving symmetries. So symmetry considerations can narrow down the possibilities, but don't seem to fully fix all details. The fine-tuning mystery remains one of the most perplexing aspects of physical law. We've discovered that our universe's laws and constants fall within narrow ranges permitting complexity. This either reflects purposeful design or selection from a multiverse, or something about logical necessity, or perhaps just brute luck. None of these explanations is entirely satisfying. Design raises the question of the designer's nature and origins. Multiverse theories face empirical and conceptual challenges. Necessity seems difficult to establish and wouldn't explain why anything physical exists, and brute luck, while possible, seems like giving up on explanation just when things get interesting. Underlying all these debates is the deeper puzzle: why should there be consistent laws at all? Even in a multiverse, each universe presumably follows some laws, however different from ours. Even a designing God would need to implement laws somehow, choose mechanisms to achieve goals. The existence of lawfulness itself, the fact that reality operates according to principles rather than complete chaos, is perhaps the most fundamental fine-tuning of all. The mathematical nature of reality, why math works. One of the most remarkable features of physical laws is that they can be expressed in the language of mathematics, not just approximately or vaguely, but with extraordinary precision. The universe seems to operate according to mathematical principles, responding to equations with numerical accuracy that often surpasses our ability to measure. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, is a profound clue about the nature of reality itself. But it's also deeply puzzling. Why should the universe obey mathematical laws? What is the relationship between abstract mathematical concepts and physical reality? Consider what happens when physicists discover a new law. They observe some pattern in nature, how objects fall, how planets orbit, how light refracts. Then they look for a mathematical relationship that captures this pattern. They might try various equations, adjusting parameters, until they find one that fits the data. But remarkably, once they have that equation, it doesn't just describe what they've already seen. It predicts new phenomena, often in regimes far beyond the original observations. Isaac Newton discovered his law of gravitation by trying to explain planetary orbits and falling objects. The mathematical form he found, force proportional to the product of masses and inversely proportional to the square of distance, was chosen to match observations. But this same equation then predicted the existence of objects beyond the known planets, explained the tides, accounted for subtle variations in the moon's motion, and much more. The mathematics led the way, revealing aspects of nature that hadn't yet been observed. James Clerk Maxwell unified electricity and magnetism into 4 elegant equations. These equations predicted that electromagnetic waves should exist and travel at a specific speed. That speed turned out to equal the measured speed of light, revealing that light itself is an electromagnetic wave. The equations then predicted the existence of electromagnetic waves at other frequencies, radio waves, microwaves, X-rays, all later discovered. Maxwell didn't set out to predict these things. The mathematics forced them upon him. General relativity provides another striking example. Einstein's field equations relating the curvature of spacetime to the distribution of matter and energy were constructed to match known facts like the orbit of Mercury. But solving these equations in various scenarios led to predictions of strange phenomena: black holes, gravitational waves, the expansion of the universe, gravitational lensing. All of these predictions, which seemed bizarre when first made, were later confirmed by observation. The mathematics revealed aspects of reality that Einstein himself sometimes found hard to believe. Quantum mechanics is perhaps the most dramatic case. The theory began with empirical observations about atomic spectra and the behavior of electrons, but the mathematical framework developed to explain these observations, wave functions, operators, Hilbert spaces, led to stunning predictions. It predicted antimatter before any was observed, It predicted quantum entanglement, which Einstein famously called spooky action at a distance, now verified in countless experiments. It predicted quantum tunneling, the Casimir effect, the structure of the periodic table. The mathematics of quantum mechanics is strange and counterintuitive, yet it describes reality with incredible accuracy. Why should this work? Why should equations invented or discovered to explain one phenomenon apply so broadly? Why should mathematical relationships have such predictive power? Wigner argued that this effectiveness is fundamentally mysterious, a miracle we neither understand nor deserve. Mathematics, he noted, is developed according to criteria of internal consistency and aesthetic appeal, not empirical adequacy. Mathematicians create theorems and structures because they're beautiful or interesting, not because they'll describe reality. Yet time and again, these abstract creations turn out to be exactly what physics needs. One response is to say that mathematics is inherent in nature, that the universe is fundamentally mathematical in character. This is the position Galileo took when he wrote that the book of nature is written in the language of mathematics. According to this view, we discover mathematics when we do mathematics, just as we discover physical laws when we do physics. Both are aspects of an objective reality that exists independently of human minds. Physicist Max Tegmark has defended a particularly bold version of this idea, the mathematical universe hypothesis. Tegmark argues that physical reality doesn't just behave according to mathematical laws, it is mathematical. The universe is literally a mathematical structure, and what we call physical properties are just features of that structure. Matter and energy aren't separate from mathematics, they're mathematical entities. This view dissolves the mystery of mathematics' effectiveness. Mathematics describes reality perfectly, because reality is mathematics. The mathematical universe hypothesis is intellectually provocative, but it faces challenges. For one thing, it seems to multiply entities beyond necessity. Why say that reality is mathematical rather than just that it behaves mathematically? The distinction might seem semantic, but it matters. If reality is mathematical, then everything that's mathematically possible exists somewhere, leading to an extravagant multiverse of all consistent mathematical structures. This raises questions about why we experience this particular mathematical structure rather than others. Another response emphasizes evolutionary adaptation. We've evolved minds capable of mathematical thinking because the universe has mathematical structure, and understanding that structure conferred survival advantages. Our ability to count, to recognize geometric patterns, to think about proportions and rates. These cognitive tools helped our ancestors track prey, navigate landscapes, coordinate social groups. Mathematics, on this view, isn't miraculously suited to describing nature. We developed mathematical intuitions because our environment already had mathematical structure, and brains that could model that structure were more successful. But this doesn't fully explain mathematics' effectiveness. Evolution would tune our mathematical intuitions to the scales and contexts relevant to survival, counting to 20, estimating distances, predicting simple projectile motion. Yet we've developed mathematical frameworks far beyond evolutionary utility. We understand infinite sets, complex numbers, non-Euclidean geometries, abstract algebras. These concepts bear no obvious relation to survival on the African savanna, yet they turn out to be crucial for describing nature at very different scales. The very small, quantum mechanics, the very fast, relativity, the very massive, cosmology. Evolution can't explain why these abstract mathematical structures we've invented through pure reason apply to physical domains our ancestors never encountered. Another perspective suggests that we're seeing selection bias. We notice and celebrate cases where mathematics successfully describes nature, but we forget or downplay cases where it doesn't. Perhaps mathematics only describes certain idealized or simplified aspects of reality, and the real world is far messier. We make measurements that inevitably have uncertainties. We develop theories that are approximations, valid only under certain conditions. Real objects aren't perfect spheres or point particles. Real processes aren't exactly linear or smooth. The mathematics describes simplified models, not reality itself. There's truth to this. Physicists do simplify and idealize. They ignore air resistance, treat planets as point masses, assume perfect conductors and ideal gases. But the remarkable thing is how accurate these mathematical models are despite the simplifications. We can calculate planetary orbits centuries in advance with stunning precision. We can design bridges and circuits that work exactly as the equations predict. We can build lasers and superconductors and GPS systems based on quantum mechanical and relativistic calculations. The mathematics isn't just a crude approximation, it captures something deep about how nature operates. Some philosophers argue that mathematics' effectiveness reflects the structure of human cognition rather than the structure of the world. We impose mathematical patterns on nature because that's how our minds work. We see regularities and systematize them mathematically, not because nature is fundamentally mathematical, but because mathematical thinking is our primary tool for understanding. In this view, the universe might not be inherently mathematical, but we can only know it through mathematical concepts, so it appears mathematical to us. But this cognitive view struggles to explain why mathematics works so well for prediction. If we're merely imposing mathematical structure on formless reality, why should that structure successfully predict new phenomena? When Maxwell's equations predicted radio waves, or when general relativity predicted gravitational waves decades before their detection, the mathematics wasn't just organizing existing observations, it was revealing new facts about reality, facts later confirmed. That suggests the mathematics is latching onto something objective, not just reflecting our mental structures. Perhaps the answer lies in recognizing that not all mathematics describes reality, only certain types. Mathematics as a whole is vastly larger than the portion used in physics. Most mathematical structures don't correspond to anything physical. So when we find a mathematical framework that does describe nature, we're not seeing that all mathematics applies to reality, but that some special mathematical structures do. The mystery then becomes, what makes these structures special? One possibility is that the mathematics used in physics tends to be relatively simple and symmetric. Physicists look for elegant equations, for patterns with symmetry and parsimony. This isn't just aesthetic preference. Experience has shown that simple symmetric laws tend to be more fundamental and more broadly applicable. Perhaps reality at a basic level is indeed simple and symmetric, and so the mathematics that describes it effectively shares these qualities. Symmetries play an enormous role in modern physics. Conservation of energy follows from symmetry under time translations. Conservation of momentum follows from symmetry under spatial translations. Conservation of angular momentum follows from rotational symmetry. Gauge symmetries underlie the standard model of particle physics. Einstein's field equations embody the symmetry of general covariance. Many of the most successful theories are built around identifying relevant symmetries and deriving their consequences. This suggests that physical laws are constrained by symmetry requirements, and symmetries are mathematical structures. Perhaps mathematics is effective because reality is symmetric and symmetries are inherently mathematical. But this pushes the question back: why is reality symmetric? Why should nature respect these particular patterns of invariance? Another intriguing connection involves information. Some physicists and cosmologists have proposed that information is fundamental, that physical laws are ultimately about how information is processed and preserved. Quantum mechanics can be formulated as a theory about the transformation of information encoded in quantum states. Thermodynamics is about the statistical properties of information at macroscopic scales. Even gravity might be connected to information through holographic principles that relate space-time structure to information on boundary surfaces. If physics is fundamentally about information, that could help explain mathematics' role. Information theory is intrinsically mathematical. Operations on information, constraints on how it can flow and transform, are naturally expressed in mathematical language. So if physical laws are information theoretic principles, they would necessarily be mathematical. But what is information in this fundamental sense? We usually think of information as something encoded in physical systems, bits in a computer, ink patterns on paper, neural activation patterns in brains. If information is supposed to be more fundamental than these physical substrates, what exactly is it? Unless we can answer that, invoking information as an explanation for physical law may just be relabeling the mystery. The deeper puzzle is that mathematics seems to exist in some sense independently of physical reality. Mathematical truths, like 2 + 2 = 4, or there are infinitely many prime numbers, would be true even if the physical universe didn't exist. They're not contingent facts that could have been otherwise. They're necessary truths, following from the logical structure of mathematical concepts. Yet these necessary, abstract, truths somehow constrain and describe the contingent, concrete physical world. How can abstract entities reach out and govern physical processes? Platonism offers one answer. Mathematics exists in a realm of perfect forms, and physical reality is a kind of imperfect reflection or instantiation of mathematical structures. But this seems to multiply mysteries. We now need to explain this Platonic realm, how it relates to physical reality, and how our minds can access it. The Platonist picture provides a metaphor more than an explanation. Anti-Platonists argue that mathematics doesn't exist independently, but is a human construction, a formal system we've invented for our purposes. But then the effectiveness of mathematics becomes even more mysterious. How could our inventions describe nature so accurately? It would be like inventing a random language and discovering that nature already speaks it fluently. Perhaps the most honest answer is that we don't know why mathematics describes reality so well. We can point to various factors: evolutionary pressures that shaped our mathematical intuitions, symmetries inherent in physical laws, the universality of certain logical structures, the role of information. But none of these fully explains the extraordinary precision and predictive power of mathematical physics. The universe operates according to mathematical principles, and mathematical structures developed for their own sake often turn out to describe aspects of reality. These are facts, but they're facts that remain deeply puzzling, hints of a relationship between mathematics and physics that we've barely begun to understand. Alternative explanations, multiverse and other theories. As we grapple with the question of why the universe has laws at all, and why these particular laws, several alternative explanations have emerged beyond traditional design or brute fact positions. The most developed and discussed of these alternatives is the multiverse hypothesis, though other creative proposals deserve consideration as well. Each attempts to make sense of our universe's apparent fine-tuning and lawfulness without invoking a designer or accepting inexplicable coincidence. The multiverse concept comes in several distinct forms, not all compatible with each other. The simplest version is the quilted multiverse, based on the possibility that space is infinite. If space extends infinitely in all directions, and if quantum mechanics is correct that there are only finitely many possible quantum states in any finite volume, then eventually patterns must repeat. Somewhere far beyond our observable universe, there must be another region configured exactly like ours, down to the quantum level. There must be another version of you reading these words. In fact, there must be infinitely many such regions. This quilted multiverse doesn't explain the laws of physics. Every region follows the same laws, but it does mean that anything that can happen, given those laws and quantum mechanics, does happen somewhere. The universe as a whole samples all possibilities, realizing every possible arrangement of matter and energy compatible with the fundamental laws. More relevant to the fine-tuning problem is the inflationary multiverse, arising from eternal inflation theory. The idea starts with cosmic inflation, a brief period of exponentially rapid expansion that the universe underwent in its first fraction of a second. Inflation was proposed to explain certain puzzling features of our universe: why it's so uniform in different directions, why it's spatially flat, why we don't see certain exotic particles predicted by particle physics theories. Inflation theory is now widely accepted based on observations of the cosmic microwave background, the relic radiation from the early universe. The pattern of tiny temperature fluctuations in this radiation matches predictions of inflationary models remarkably well, but many inflation models have a strange property. Once inflation starts in some region, it never completely stops everywhere. Quantum fluctuations make the inflation field vary randomly from place to place. In some regions, the field drops to lower values, and inflation ends, creating what we'd call a universe. But in other regions, the field fluctuates upward and inflation continues, driving those regions to expand exponentially, while producing new regions where inflation ends. This process can continue forever. Eternal inflation. The result is a vast, perhaps infinite structure, where bubble universes continually form in an eternally inflating background. Each bubble has its own Big Bang when inflation ends there, its own subsequent evolution, its own galaxies and stars. These bubbles are causally disconnected from each other because the space between them is inflating so rapidly that no signal can cross from one bubble to another. We live in one such bubble, which we call the universe, but it's just one among countless others. Here's where the connection to fine-tuning comes in. In many theories, particularly string theory, The low-energy physics that emerges after inflation can differ from bubble to bubble. String theory predicts many possible stable configurations of extra dimensions and field values, perhaps 10 to the 500 different possibilities, creating what's called the landscape. Each configuration corresponds to different effective laws and constants that would be observed by low-energy physics like chemistry and biology. If eternal inflation realizes all these possibilities, creating bubbles with every possible set of laws and constants from the landscape, then we live in one that happens to have laws permitting complexity and observers. The fine-tuning is explained anthropically. Most bubbles are sterile and simple, but we obviously couldn't exist there, so we necessarily find ourselves in one of the rare bubbles with right conditions for life. It's like a vast lottery, where most tickets lose but someone must win, and naturally that someone exists to wonder at their luck. The inflationary multiverse is appealing because it emerges from theories, inflation and string theory, that were developed for other reasons and have some empirical support. We didn't invent the multiverse just to solve the fine-tuning problem. It's a consequence of taking seriously our best theories of early universe physics and fundamental particles. If those theories are on the right track, a multiverse seems unavoidable. But the inflationary multiverse faces significant challenges. First, eternal inflation is hard to describe precisely. The usual language of probabilities doesn't apply straightforwardly when there are infinitely many instances of everything. If there are infinitely many bubbles with your exact properties, and infinitely many with slightly different properties, how do you calculate which is more probable? Physicists have proposed various measures, ways of assigning probabilities in an infinite multiverse, but no consensus has emerged, and different measures give different predictions. Second, some critics argue that eternal inflation undermines itself. If inflation produces infinitely many bubbles with all possible properties, then predictions become impossible because every outcome occurs somewhere. Inflation doesn't tell us what we should expect to observe. It says all observations occur. Paul Steinhardt, one of inflation's original developers, has become a vocal critic on these grounds, arguing that a theory making all outcomes equally likely makes no predictions and thus isn't science. Defenders of eternal inflation respond that predictions are still possible using anthropic reasoning. We should calculate probabilities not over all bubbles but over all observers in all bubbles, weighting by how many observers experience each set of laws. If most observers experience universes with certain features, we should expect to observe those features. This is the self-sampling assumption. Reason as if you're a randomly selected observer from all possible observers. But this leads to puzzles of its own, like the Boltzmann brain problem, where thermodynamic fluctuations in dead universes might produce more observers than arise through normal evolution in life-permitting universes. Third, the inflationary multiverse isn't directly observable. We can't see other bubbles or travel to them. We can only test inflation by its predictions for our bubble. This leads critics to question whether the multiverse is truly scientific or merely speculative metaphysics. Defenders argue that we can accept unobservable entities if they're part of our best theories, just as we accept quarks despite never observing an isolated quark or the unseen far side of the moon. If our best theories of inflation and string theory predict a multiverse, that's reason to believe in it. Another multiverse concept comes from quantum mechanics itself. The many-worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum measurement causes the universe to split into multiple branches. In one branch, you observe the particle spin up. In another branch, you observe spin down. Both outcomes occur in different but equally real branches of the wave function. This interpretation takes quantum mechanics completely literally, avoiding the mysteries of wave function collapse by saying the wave function never collapses. All possibilities are realized in a vast superposition. The quantum multiverse doesn't directly address fine-tuning since all branches have the same laws. But it represents a radically different picture of reality where the familiar world we experience is just one branch among countless others, all existing simultaneously in a high-dimensional configuration space. And some speculative theories combine quantum many-worlds with cosmological ideas, suggesting the Big Bang itself might have been a quantum event producing many branches with different properties. Beyond multiverse theories, other speculative proposals attempt to explain the laws of nature. Lee Smolin has proposed cosmological natural selection, analogous to biological natural selection but acting on universes. The idea is that black holes might give birth to new universes with slightly different laws, creating a kind of reproduction. Universes that produce many black holes have more offspring. Over vast numbers of generations, laws would evolve toward configurations that maximize black hole production. Intriguingly, black hole formation might require similar conditions to those needed for complex structures and life, so selection for black holes might indirectly select for life-permitting laws. Cosmological natural selection is clever, but it faces problems. We don't know if black holes really spawn new universes, or how their laws might differ from the parent universe. The theory makes predictions. Universes selected for black hole production should have certain properties, but these predictions are debatable and haven't been clearly confirmed or refuted. And the theory still requires some initial laws and an initial multiverse to get the process started, so it doesn't fully explain why there are laws at all. The simulation hypothesis proposes that our universe is actually a computational simulation run by an advanced civilization. The laws of physics are then just the rules of the simulation, coded by the simulators. This explains fine-tuning. The simulators chose laws that would produce interesting results, perhaps specifically creating conditions for life to emerge. It also explains why the universe seems mathematical. Mathematics is the language of computation. The simulation hypothesis is fun to contemplate, but it has serious issues as an explanation. First, it just pushes the mystery up a level. What about the simulator's universe? Why does it have its laws? If their universe is also a simulation, we have an infinite regress. If it's not, then we haven't really explained lawfulness, just claimed our particular laws are artificial. Second, the simulation hypothesis doesn't obviously make testable predictions beyond what standard physics already predicts. Unless we discover glitches in the simulation, or find evidence of its computational substrate, it's not clear how we'd ever confirm or refute the idea. And if the simulators are sufficiently advanced, they could presumably hide all evidence that we're in a simulation. This makes the hypothesis empirically equivalent to the claim that we're not in a simulation. They explain the same observations, which raises questions about whether there's a real difference between the two scenarios. Yet another approach, pursued by some philosophers and physicists, involves top-down cosmology or quantum cosmology. These frameworks use quantum mechanics to describe the universe's initial conditions, proposing that the universe emerged from a quantum superposition or quantum fluctuation. Stephen Hawking and James Hartle developed a no-boundary proposal in which the universe's beginning is described by a wave function, defined over all possible initial configurations. The universe doesn't have a beginning in the traditional sense, but emerges from a timeless quantum state. In Hawking's later work with Thomas Hertog, they proposed that this quantum approach reduces the multiverse, making predictions more tractable. Rather than eternally inflating into all possible configurations, the universe selects from a more limited set of possibilities consistent with observations. This would preserve some of multiverse's explanatory power, while avoiding some of its conceptual problems. But quantum cosmology is highly speculative and involves concepts, like a wave function for the entire universe, that are difficult to interpret and impossible to directly test. All these alternative explanations grapple with the same fundamental tension. We observe a universe with specific, apparently fine-tuned laws. We can either accept this as brute fact, invoke a designer, propose a mechanism that generates multiple universes, or try to show the laws are somehow necessary. Each approach has costs and benefits. Design raises questions about the designer. Multiverse theories face probability puzzles and empirical challenges. Necessity requires showing that other laws are impossible, which seems difficult to establish. And brute fact feels like giving up on explanation. Perhaps no single explanation will suffice. Perhaps reality is genuinely strange, involving aspects of all these ideas. Maybe there is a multiverse, and the appearance of design reflects anthropic selection, and underlying it all are mathematical necessities we haven't yet grasped. Or perhaps the question itself is ill-posed, reflecting assumptions about explanation and causation that don't apply to the universe as a whole. These possibilities remain open as physicists and philosophers continue to wrestle with the deepest questions about nature's lawfulness. The deepest question: why something rather than nothing? At the foundation of all questions about physical laws lies perhaps the most profound question: philosophy and science have ever confronted. Why is there something rather than nothing? This question cuts deeper than asking why the laws are what they are, or why the constants have their particular values. It asks why there's anything at all for laws to govern. Why does existence exist? The question was crystallized by the German philosopher Gottfried Wilhelm Leibniz in the early 18th century, though thinkers had pondered it for millennia before. Leibniz formulated it as part of his principle of sufficient reason, the idea that everything must have a reason or explanation for why it is rather than isn't. For Leibniz, the answer involved God. The universe exists because God chose to create it, being the most perfect and good possible being. God's nature provided the ultimate sufficient reason for existence itself. But this answer raises immediate questions. Why does God exist? If God exists necessarily, by virtue of what God is, then what makes necessary existence possible? And why should we believe that an entity with necessary existence is coherent or actual? These questions have troubled theologians and philosophers for centuries. Saying God exists necessarily seems to just assert what needs to be explained. It declares that one particular thing, God, doesn't need an explanation, but without showing why that exemption is justified. We might try a similar move without invoking God. Perhaps the universe itself exists necessarily. Perhaps there couldn't have been nothing. Philosopher Baruch Spinoza took this view, arguing that the universe is a necessarily existing substance. Its existence follows from its nature just as mathematical truths follow from the nature of numbers. The universe must exist in the same way that 2 + 2 must equal 4. But why should we accept that the universe exists necessarily? We can conceive of nothing existing. At least we think we can. The universe seems contingent, like it might not have been here. Laws might have been different or absent. Particles might never have formed. The Big Bang might never have occurred. To claim the universe exists necessarily is to claim all these alternatives are impossible, that the actual configuration of reality is the only possibility. That seems like an extraordinary claim requiring extraordinary justification. Some physicists have tried to answer the question using quantum mechanics. Lawrence Krauss's book A Universe from Nothing argues that universes can spontaneously emerge from quantum vacuum fluctuations. In quantum field theory, what we call empty space isn't truly empty. Virtual particles constantly pop into existence and disappear. The energy to create these particles is borrowed from quantum uncertainty, which allows brief violations of energy conservation. Krauss and others suggest that an entire universe could emerge the same way, a quantum fluctuation creating space, time, matter, and energy from nothing. But critics point out that this doesn't really explain something from nothing. The quantum vacuum isn't nothing. It's a physical state with properties, governed by quantum field theory, embedded in space-time. Virtual particles aren't nothing. They're fluctuations in quantum fields, which are something. Krauss's nothing is actually a complex structured something. The explanation assumes quantum mechanics, space-time, and field theory, none of which is nothing. It might explain how a universe could emerge from a pre-existing quantum state, but it doesn't explain why there's a quantum state rather than nothing at all. Sean Carroll, another prominent physicist, has argued that the question might not have an answer, or more, precisely, that insisting on an answer reflects confused thinking about causation and explanation. When we ask why about ordinary events, we're asking about causes within the universe. Why did the window break? Because a ball hit it. Why did the ball hit it? Because someone threw it. This chain of causes makes sense because each step refers to earlier events in space-time, events causally connected to later ones. But the universe as a whole doesn't exist in time in the same way. It doesn't have a cause in the ordinary sense because causes precede their effects, and nothing precedes the universe. Asking why the universe exists is like asking what's north of the North Pole. The question assumes a framework, causation in time, that doesn't apply to the thing being asked about. Carroll suggests that the universe just is, and seeking some deeper explanation reflects a failure to accept that explanation must bottom out somewhere. This response is unsatisfying to many. It feels like giving up, declaring the fundamental question unanswerable, not because we've reached the limits of human knowledge, but because we've decided the question is illegitimate. Surely we can meaningfully ask why anything exists. Even if there's no causal explanation in the usual sense, there might be some other form of explanation, logical, mathematical, metaphysical, that makes sense of existence itself. Robert Nozick, in his book Philosophical Explanations, proposed several creative possibilities. One is the principle of fecundity. All possible worlds exist because existence is generative, productively outstripping non-existence. Another is self-subsumption. There's a principle that applies to itself and thereby explains its own truth. Yet another involves what he called the nothingness force. Nothingness is unstable and naturally transforms into something. These ideas are provocative, but they're more thought experiments than developed theories. They gesture at possible forms explanation might take without fully working them out. The physicist Alex Vilenkin has explored scenarios where the universe emerges from nothing in a more literal sense than Krauss's quantum vacuum. Using quantum cosmology, Vilenkin describes the universe tunneling into existence from a state with no space, time, or matter. The wave function describing this transition doesn't require pre-existing structures. It's a mathematical description of how something can arise from genuine absence. However, this approach still assumes quantum mechanics and certain mathematical structures. The wave function exists in some sense, even if physical space and time don't, so we haven't fully escaped from something into nothing. Perhaps the issue is that nothing is incoherent. We can say the word, but can we really conceive of it? When we try to imagine nothing, we imagine empty space. But empty space is something. It's space. We might try to imagine the absence of space, but then we're imagining a situation from some viewpoint, and that viewpoint is something. We might imagine blackness, but blackness is a visual experience, which is something. The absence of all things might be genuinely inconceivable, because our concepts always refer to things that exist. If nothing is inconceivable, then perhaps the question, why is there something rather than nothing, is ill-formed. It assumes nothing is a possible alternative to something, but maybe it isn't. Maybe existence is necessary not because of any particular thing's nature, but because non-existence is logically impossible. In that case, there's no puzzle. Something must exist because nothing is not a genuine possibility. But this seems too quick. Even if we can't fully imagine nothing, we can certainly understand the concept. We understand absence, negation, zero. The absence of all things seems like it should be logically possible, even if it's not psychologically conceivable in full detail. And even if existence is necessary, that would still leave the question of why this particular form of existence rather than some other. One intriguing observation is that there seem to be many more possible somethings than there are ways to be nothing. If there's nothing, there's only one way things can be, the absence of everything. But if there's something, the possibilities explode. There could be this universe or a different one. There could be multiple universes or a multiverse. There could be abstract entities or concrete ones or both. The space of possible something vastly exceeds the single state of nothingness. From this perspective, something rather than nothing might be probabilistically favoured. If we imagine randomly selecting from all possible ways reality could be, we're far more likely to hit some configuration of something than the one configuration of nothing. This doesn't fully explain why there's something. It still assumes a space of possibilities and some kind of selection process, but it suggests that something might be more natural than nothing in some sense. Another angle comes from self-reference and self-causation. Some philosophical traditions, particularly in Eastern philosophy, explore ideas where existence explains itself, where the question of why something exists is answered by the nature of existence itself. The universe exists because existence is inherently generative, because being brings forth being. This is not causation in the usual sense, but something more fundamental. These ideas are difficult to make precise, but they gesture toward a form of explanation where the deepest truths are self-sustaining, grounding themselves rather than requiring an external foundation. The question might also be approached through modal logic, the logic of necessity and possibility. Perhaps all possible worlds exist, and our universe is one among infinitely many. The question then becomes not why there's something rather than nothing, but why there's everything rather than just one thing or nothing. This many worlds metaphysics, sometimes called modal realism, has been defended by philosopher David Lewis. On this view, possible worlds aren't just abstract ideas, they're concrete realities, just as real as our world. We call our world actual merely because we're in it, not because it's special. Modal realism dissolves the original question by making existence maximal. It's not that something exists rather than nothing, but that everything exists. There is no nothing because all possibilities are realized. But this raises all the problems of multiverse theories, plus additional puzzles. Why should all possibilities exist? What grounds this plurality? And isn't the claim that absolutely everything exists itself something that needs explanation? We might also consider that the question assumes a God's eye view, a perspective outside existence from which we can contemplate existence versus non-existence, but any perspective capable of asking the question is already within existence. We can't actually step outside being to evaluate it. The question might be meaningless because it requires an impossible vantage point, yet the question persists. We can't shake the intuition that there's something deeply puzzling about the fact of existence. Even if we accept that some brute facts are unavoidable, the existence of reality seems like the most fundamental fact of all. And even if we can't fully answer it, wrestling with the question illuminates deep truths about causation, explanation, possibility, and the limits of human understanding. Perhaps ultimately we must accept mystery. Not every question has an answer. Some questions might be unanswerable in principle, not because we lack the tools, but because they're questions about the framework within which answers exist. Asking why there are physical laws, why there's something rather than nothing, might be like asking what colour Wednesday is, or whether justice weighs more than love. The question applies categories that don't fit the subject. Or perhaps the answer is out there, waiting to be discovered. Perhaps some genius will show that existence is logically necessary, or that nothing is incoherent, or that the quantum wave function of the universe explains itself. Perhaps we'll develop entirely new frameworks for thinking about existence that make the question tractable. The history of human thought is full of questions that seemed unanswerable until someone found the right way to approach them. What seems clear is that the question, why is there something rather than nothing, is intimately connected to the question of why there are laws. Laws govern how things behave, but laws themselves are something rather than nothing. Any explanation for laws must ultimately confront the deeper question of existence itself, and conversely, any explanation for existence must address why existence takes the form it does, lawful, mathematical, structured, rather than being chaotic or formless. These questions sit at the boundary between physics and philosophy, between empirical science and pure thought. They can't be answered by observation or experiment alone, yet they can't be answered by armchair reasoning either. They require the tools of both disciplines, the conceptual clarity and logical rigor of philosophy, and the empirical grounding and mathematical precision of physics. Neither alone is sufficient. Together, they allow us to probe the deepest mysteries, even if complete answers remain elusive. Conclusion and reflection. As we drift toward the end of our journey, let's gather together the threads we've followed through this long night of contemplation. We've explored one of humanity's most profound questions. Why does the universe have laws at all? Why is there order rather than chaos, pattern rather than randomness, comprehensibility rather than inscrutability? We've seen that physical laws are remarkably universal, applying everywhere and everywhere across the vast cosmos. The same forces that govern a falling apple on Earth also govern the motion of distant galaxies. The same quantum mechanics that explains atomic spectra here also explains stellar fusion billions of light years away. This universality isn't something we should take for granted. It's deeply mysterious, a core feature of reality demanding explanation. We've traced how humans discovered these laws, from ancient philosophers wondering about nature's principles to modern physicists probing the quantum realm and cosmic scales. Each generation built on the insights of previous ones, slowly revealing more of nature's mathematical structure. Newton unified celestial and terrestrial physics. Maxwell unified electricity and magnetism. Einstein unified space and time, then showed gravity as space-time curvature. The Standard Model unified 3 of the 4 fundamental forces. The journey has been one of finding deeper simplicities beneath apparent complexities, unifying what seemed separate. We've examined the 4 fundamental forces, gravity, electromagnetism, the strong force, the weak force, that govern all physical interactions. Each operates according to precise mathematical rules, acts over specific ranges, exhibits particular strengths. Together they orchestrate the cosmic dance, from subatomic processes to the evolution of galaxies. They're not random or arbitrary, but highly structured, following patterns that our minds can grasp and our equations can describe. We've considered the fundamental constants, those special numbers appearing in physics equations that don't change across space or time. The speed of light, Planck's constant, the gravitational constant, the electron charge, the masses of particles, these define reality's parameters, and remarkably they seem fine-tuned, falling within narrow ranges that allow for complex structures including life. Change them even slightly and the universe becomes sterile and simple. This apparent fine-tuning demands explanation. Is it evidence of design, a cosmic engineer deliberately choosing parameters? Or does it reflect anthropic selection from a vast multiverse where all possibilities are realized and we naturally find ourselves in a life-permitting bubble? Or might the constants be uniquely determined by some deeper principle we haven't discovered, making alternatives impossible? Each explanation has strengths and weaknesses. Each raises new questions. We've marveled at the unreasonable effectiveness of mathematics in describing physical reality. Why should abstract patterns invented by mathematicians for purely aesthetic reasons turn out to govern how particles interact and stars shine? Why should the universe obey mathematical laws at all? This suggests some deep connection between mathematical structure and physical reality, though the nature of that connection remains unclear. We've explored multiverse hypotheses, particularly eternal inflation, which posits countless bubble universes with different properties. If this is correct, fine-tuning becomes less mysterious. We simply happen to inhabit one of the rare bubbles where complexity is possible. But multiverse theories face challenges. They're difficult to test, lead to probability puzzles, and might be seen as giving up on explaining our universe by multiplying universes. And we've confronted the deepest question of all. Why is there something rather than nothing? This question underlies all others. Before asking why the laws are what they are, we must ask why there are any laws, any reality, anything at all. No one has a fully satisfying answer. Some say God created everything. Some say existence is necessary. Some say the question is meaningless. Some say it has no answer. The mystery remains. What can we conclude from this journey through these profound questions? Perhaps most importantly, we should feel a sense of wonder. The universe exists, operates according to laws, and these laws are comprehensible to creatures like us. This is extraordinary, not inevitable. Reality could have been incomprehensible chaos. It could have been static and unchanging. It could have been so different that minds could never evolve to contemplate it. Instead, we find ourselves in a cosmos governed by elegant mathematical principles that our finite minds can partially understand. This understanding has practical benefits. It lets us build technologies, predict eclipses, cure diseases, explore space. But beyond utility, understanding the universe's laws connects us to something larger than ourselves. When you learn that the same atoms making up your body were forged in ancient stars, that you're literally made of stardust, something shifts in your perspective. When you realize that the mathematical patterns you learn in school describe not just abstract ideas, but the actual fabric of reality, mathematics becomes more than symbols on paper. When you grasp that the entire observable universe expanded from a hot, dense state 13.8 billion years ago, following laws that still govern every atom today, the past becomes more vivid and the future more wondrous. We should also feel humility. For all our progress, fundamental mysteries remain. We don't know why the laws are what they are. We don't know why the constants have their values. We don't understand the relationship between mathematics and physical reality. We haven't reconciled quantum mechanics with general relativity. We don't know what dark matter or dark energy is. We don't know whether there's a multiverse or if our universe is all there is. We don't know why there's something rather than nothing. These gaps in our knowledge aren't failures but opportunities. Every answered question reveals new questions. Every mystery solved exposes deeper mysteries. This is what makes science exciting. There's always more to discover, always deeper to dig, always further horizons to reach. The universe won't be fully understood in our lifetimes, perhaps not ever. But the journey of discovery continues, each generation adding its pieces to the puzzle. We should remain open to different perspectives. Scientists, philosophers, theologians, artists, all have insights to offer about the nature of reality and why it has the form it does. No single discipline has a monopoly on truth. Physics can tell us what the laws are and how they operate. Philosophy can clarify what we mean by laws and why certain explanations satisfy us or fall short. Theology can explore what purpose or meaning might underlie existence. Art can capture the emotional resonance of our cosmic condition. We need all these perspectives in conversation with each other to make progress on the deepest questions. And finally, we should act with gratitude. Whatever the ultimate explanation, we find ourselves existing in a universe with laws that make complexity possible, that allow stars to shine and planets to form, that permit the chemistry of life, that make consciousness possible. We're here, able to ask these questions, able to discover nature's patterns, able to create meaning and beauty. That's a gift, regardless of whether there's a giver. As you drift towards sleep, let these thoughts settle gently into your mind. The universe operates according to laws. You are part of that universe, made of its matter, governed by its forces, participating in its unfolding. The atoms in your body obey quantum mechanics. The electrical signals in your neurons follow Maxwell's equations. Gravity keeps you grounded. The weak force powers the sun that warmed your day. You're continuous with the cosmos, a local expression of its fundamental patterns. Why the universe has laws remains mysterious, but that mystery enhances rather than diminishes the wonder of existence. We live in a comprehensible universe, one that rewards curiosity with understanding. That alone is remarkable, that alone deserves our awe. Sleep. Well, knowing you're part of something vast and lawful and beautiful. And if you found this exploration meaningful, consider subscribing to the Dreamy Science Guy, so we can continue these journeys together. Good night. Additional exploration, the nature of physical law. Before we truly rest, let's explore a bit deeper into what it means for something to be a physical law. This question sits at the intersection of science and philosophy, and understanding it better helps illuminate why the existence of laws is so mysterious. When physicists say something is a law of nature, they're making several claims at once. They're saying that nature behaves in a regular, predictable way. They're saying this regularity can be expressed mathematically. They're saying the pattern holds universally across space and time, and they're implying a kind of necessity. The law doesn't just describe what does happen, but what must happen. But what grounds this necessity? In human laws, there are lawmakers, who decree rules and enforcement mechanisms that ensure compliance. A speed limit of 65 miles per hour exists because legislators voted for it, and police officers enforce it. But physical laws have no legislators, no enforcement agents. Electrons don't follow the rules of quantum mechanics because someone told them to, or because they'll be punished for disobedience. They follow these rules because that's what it means to be an electron in this universe. This suggests that physical laws aren't really laws in the prescriptive sense at all. They're descriptions of how things inherently behave. The law of gravity doesn't make masses attract, and the law of gravity is our way of describing that attraction. The distinction matters because it shifts the mystery. The question isn't who or what enforces the laws, but why do things have the natures they do? Why do masses attract? Why do like charges repel? Why do quantum systems evolve according to Schrödinger's equation? One philosophical position, called humanism after philosopher David Hume, denies that there's any necessity in nature at all. According to humans, there are just events, one after another, and we notice regularities in how events follow each other. We see billiard balls colliding and moving in predictable ways, so we formulate laws of mechanics. But there's no necessary connection between cause and effect, no cosmic glue binding events together. The regularities just are, and calling them laws is a human convenience, not a deep fact about reality. If humanism is correct, then asking why there are laws is like asking why there are patterns. Patterns exist because events happen in regular ways. Why do events happen in regular ways? There might be no deeper answer. Regularity is just a brute fact about our universe. This dissolves some of the mystery, but at the cost of making the universe's orderliness seem like an astonishing coincidence. Why should events fall into patterns rather than being completely random? An opposing view, held by many philosophers of science, is that laws are indeed necessary in some sense. They're not just descriptions of what happens to occur, but constraints on what can occur. Nature genuinely follows rules. This necessitarian view takes laws seriously as fundamental features of reality. On this view, the universe isn't just regular, it's lawful, governed by principles that determine how things must behave. If this is right, then laws do require explanation, and the mystery of why there are laws is a genuine puzzle rather than a category mistake. We need to understand what makes laws necessary, what grounds their authority over nature's behavior. Various answers have been proposed. Perhaps laws flow from the essential natures of things. Electrons behave as they do because of what electrons fundamentally are. Perhaps laws reflect constraints imposed by logic or mathematics. Certain behaviors are logically required, given certain structural facts. Perhaps laws are relationships among universal properties that exist across all instances of those properties. The concept of natural kinds is relevant here. A natural kind is a category that exists in nature independently of human classification. Electron is arguably a natural kind. Electrons really form a distinct class of entities with shared properties, not just a label we've arbitrarily applied to some collection of things. If natural kinds exist, and if each kind has an essential nature that determines how its members behave, then laws might be expressions of these essential natures. The law governing electron behavior would follow from what electrons essentially are, but this raises questions about the nature of properties and essences. What makes a property natural rather than arbitrary? Why do certain properties cluster together in stable kinds? What grounds the essential nature of a natural kind? We've again pushed the question back without fully answering it. The mystery of laws becomes the mystery of natural kinds and essences. Another important distinction concerns the difference between fundamental laws and derivative laws. Some laws seem to be basic, irreducible features of nature. The laws of quantum mechanics, general relativity, and the Standard Model might be fundamental in this sense. Other laws are derivative, emerging from more basic laws when applied to special situations. The laws of thermodynamics, for instance, follow from statistical mechanics, which in turn follows from the fundamental laws governing particle behavior. If some laws are fundamental and others derivative, then explaining why there are laws requires explaining only the fundamental ones. The derivative laws exist because the fundamental laws exist and have the properties they do. This simplifies the explanatory burden. We don't need separate explanations for every law, just for the basic ones from which others flow, but it still leaves the question of why those fundamental laws exist and have their particular forms. Physicists often speak of symmetries as constraining or even determining the laws. A symmetry is an operation that leaves something unchanged. If the laws of physics are the same everywhere in space, that's a translational symmetry. If they're the same at all times, that's a temporal symmetry. If they're the same viewed from any angle, that's a rotational symmetry. These symmetries have profound consequences through Noether's theorem, which connects symmetries to conservation laws. Some theorists hope that requiring certain natural symmetries might uniquely determine the laws, or at least narrow the possibilities dramatically. If we insist that laws must be symmetric under certain transformations, Lorentz transformations, gauge transformations, general coordinate transformations, perhaps only certain mathematical structures satisfy these requirements, the laws we observe might be the only ones consistent with these fundamental symmetries. This is an appealing idea, but it faces challenges. First, why should nature respect these particular symmetries rather than others or none? The symmetries themselves require explanation. Second, symmetry requirements don't fully determine all details of laws. They constrain the form equations can take but leave many parameters free. Third, some symmetries are only approximate. The universe exhibits CP violation, for instance, meaning it's not perfectly symmetric under combined charge conjugation and parity transformation. So symmetries can't be the complete story. The role of initial conditions is also relevant. Laws tell us how systems evolve from one state to another, but they don't tell us what state the universe started in. The initial conditions at the Big Bang, the distribution of matter and energy, the values of fields, the quantum state of the universe, were special in ways not explained by the laws alone. The early universe had extremely low entropy, an ordered state from which entropy could increase. Why? The laws of thermodynamics don't demand low initial entropy. They're compatible with any initial state. Some cosmologists invoke inflation to explain this, arguing that inflation naturally produces the kind of smooth low-entropy conditions we observe. But inflation itself requires special initial conditions, a patch of space dominated by a particular field in a particular state. So the initial conditions problem might be pushed back but not solved. Others suggest the universe's initial state was actually the most probable one given quantum cosmology. But calculations of quantum probabilities for the universe are fraught with ambiguity. Initial conditions and laws together determine the universe's history. To fully explain why things are as they are, we need to explain both. If we only explain the laws, we've left half the story untold. This suggests that questions about why there are laws are intimately tied to questions about why the universe began in the state it did. Perhaps there's no sharp distinction. Perhaps what we call initial conditions are just another set of constraints on cosmic evolution, like laws but applying only at the beginning rather than throughout history. The possibility of time-varying laws or position-dependent laws is worth considering. Most physicists assume laws are the same everywhere and always, but this is an assumption, not something we've proven. We've tested that laws are stable across human timescales and across observable space, but the universe is billions of years old and vastly larger than we can see. Could laws have been different in the very early universe? Could they be different in distant regions beyond our horizon? Could they slowly evolve over cosmic timescales? If laws can vary, then their current form might be explained by some kind of cosmic evolution or selection process. Perhaps the universe passed through various regimes with different laws before settling into its present state. Perhaps laws emerge and stabilize through processes we don't yet understand, like how water settles into ice when cooled. This would make current laws contingent historical facts rather than eternal necessities, but it would still leave the question of why there are meta-laws governing how laws evolve. The relationship between laws and causation is subtle. We often think of laws as governing causal relationships. Force causes acceleration, charge creates electric field, mass warps space-time. But does causation exist independent of laws, or do laws define what causation is? If the former, laws describe causal relationships but don't create them. If the latter, asking why there are laws is equivalent to asking why there's causation. Quantum mechanics complicates the picture because it's not straightforwardly causal in the classical sense. A quantum state evolves deterministically according to Schrödinger's equation, but when we make a measurement, we get random outcomes obeying probabilistic rules. Is this truly indeterministic, with some events genuinely uncaused? Or is there some hidden layer of causation we haven't yet discovered? Different interpretations of quantum mechanics give different answers, and we don't know which is correct. If quantum mechanics is fundamentally indeterministic, then laws don't fully determine what happens, they only determine probabilities. In that case, the universe is less tightly governed by laws than classical physics suggested. There's room for chance, for outcomes that aren't necessitated by prior conditions and laws. This makes the existence of laws even more puzzling. Why should nature be partly lawful and partly random? Why not fully one or the other? The concept of emergence is also relevant. Emergent phenomena are those that arise from lower-level processes, but have their own autonomous dynamics. Temperature and pressure emerge from molecular motions, but obey their own thermodynamic laws. Life emerges from chemistry, but exhibits biological principles that aren't straightforwardly reducible to chemical laws. Consciousness emerges from neural processes, but has its own phenomenological character. If emergence is real and robust, then there might be laws at multiple levels: fundamental laws governing particles, higher-level laws governing atoms, molecular laws governing chemistry, biological laws governing life, psychological laws governing mind. Each level would have its own regularities, its own principles, potentially its own form of necessity. This would mean asking why there are laws must be answered separately for each level. Perhaps fundamental physical laws exist for one reason, while emergent laws exist for another. But emergence is controversial. Some argue it's just a useful way of talking about complex systems, not a fundamental feature of reality. According to this reductionist view, there are only fundamental laws governing fundamental entities, and all apparent higher-level laws are just patterns that emerge from these basics. If reductionism is correct, we only need to explain fundamental laws, and the mystery is somewhat simplified. If emergentism is correct, we face multiple mysteries at multiple levels. These philosophical puzzles about the nature of law, necessity, causation, and emergence aren't idle speculation. They bear directly on the question of why there are laws at all. We can't explain why laws exist without understanding what laws are, what makes them laws, what grounds their authority over nature's behavior. Different answers to these conceptual questions lead to different explanations for the existence of laws. Perhaps most fundamentally, we might question whether explanation can go all the way down. Every explanation appeals to something prior or deeper. You explain one thing in terms of another, but does this process ever end? Must there be ultimate facts that themselves have no explanation? Brute features of reality that simply are what they are? Or can we hope for a complete explanation where everything is explained by something else in a kind of circular or self-supporting structure? The principle of sufficient reason says everything has an explanation. Leibniz used this principle to argue for God's existence. The universe requires explanation, only a necessary being can provide it, therefore God exists. But the principle of sufficient reason might be false. Perhaps some facts are brute, inexplicable. Perhaps the chain of explanation must terminate somewhere, and the existence of laws is as good a stopping point as any. On the other hand, if we accept brute facts, where do we draw the line? Which facts get to be brute, and which require explanation? It seems arbitrary to say the laws are brute facts, but other things aren't. And accepting brute facts at the deepest level feels intellectually unsatisfying, like giving up just when the questions become most interesting. These are deep waters, and wading into them reveals how profoundly puzzling the existence of laws truly is. It's not a simple empirical question scientists can answer with more data and better theories. It's a conceptual question requiring philosophical analysis of what we mean by laws, necessity, explanation, and reality itself. Science and philosophy must work together, neither alone sufficient to answer the question. As we contemplate these mysteries, we might feel our minds stretching, reaching for concepts beyond our everyday experience. That's appropriate. The question of why there are laws pushes us to the limits of human understanding, to the boundaries where thought itself becomes difficult. We're asking about the foundations of everything, the most basic features of existence. It would be surprising if the answers came easily, or if we could fit them comfortably into our pre-existing conceptual frameworks. Let your mind rest now with these questions. They're the kinds of questions that humanity will likely continue asking for as long as there are minds to ask them. Each generation will approach them from new angles with new tools and discover new insights. The mystery remains, but the journey of exploration continues. And in that journey, in the very asking of these deep questions, we touch something essential about what it means to be human, to wonder, to question, to seek understanding of our place in the grand scheme of things. A final meditation, living in a lawful universe. As we approach the end of our journey through these cosmic questions, it's worth reflecting on what it means for us, practically and existentially, that we live in a universe governed by laws. This isn't just an abstract philosophical puzzle, it shapes our daily experience, our possibilities, our very existence as conscious beings. The lawfulness of the universe makes science possible. If nature didn't follow regular patterns, if the same experiment gave different results, each time for no reason, scientific knowledge couldn't accumulate. We could never predict anything, never control anything, never understand anything. The fact that we can learn about nature, that knowledge gained in one context applies in another, that today's observations inform tomorrow's predictions, all this depends on the universe being lawful. This lawfulness also makes technology possible. Every device you use, from the simplest tool to the most sophisticated computer, works because we understand and can rely on physical laws. Engineers design bridges knowing how materials respond to stress. Doctors prescribe medications knowing how molecules interact with cells. Farmers plant crops knowing how seeds respond to water and light. All technology is applied knowledge of natural law. But beyond these practical benefits, the lawfulness of the universe has deep existential implications. It means we're not at the mercy of complete chaos. Tomorrow will resemble today in important ways. The sun will rise, gravity will hold us to Earth, chemical bonds will maintain the molecules our bodies need. This reliability, this predictability, this trustworthiness of nature is what makes life possible. Yet the laws also constrain us. We can't travel faster than light, no matter how much we might want to visit distant stars. We can't violate conservation of energy, no matter how convenient perpetual motion would be. We can't escape death, because thermodynamics ensures all organized systems eventually decay. The same laws that enable our existence also limit our possibilities. This raises questions about free will and determinism. If the universe is governed by laws, if every event follows from previous events according to fixed rules, are we truly free? Or are we just complex machines, our thoughts and choices determined by the prior state of our brains, which in turn was determined by earlier states In an unbroken chain back to the Big Bang, some argue that deterministic laws are compatible with free will, that freedom means acting according to our own nature and desires, even if those are physically determined. Others insist true freedom requires indeterminism, randomness, events not fully determined by prior causes. Quantum mechanics introduces genuine randomness into the picture, but it's unclear whether this helps with free will. Random quantum events aren't under our control, so they don't seem to provide the right kind of freedom. Perhaps free will requires something beyond both deterministic and random processes, some third category of causation unique to conscious agents. Or perhaps free will is an illusion, and understanding the laws that govern our choices should lead us to rethink concepts like moral responsibility. The predictability that laws provide also shapes our emotional lives. We feel secure because we can anticipate what will happen. We make plans, invest in the future, care about long-term consequences because we trust that lawful patterns will continue. If we genuinely believed nature might become chaotic tomorrow, that gravity might stop working or chemical bonds might randomly break, we couldn't function psychologically. The reliability of laws undergirds our ability to live purposeful lives. At the same time, complete predictability would be stifling. We value novelty, surprise, creativity. We want the universe to have room for new things to emerge, for the future to be open rather than fully determined. The interplay between law and chance, between predictable patterns and unpredictable events, creates space for both order and novelty. Perhaps this balance is optimal, enough lawfulness for stability, enough openness for growth. The comprehensibility of laws, the fact that human minds can understand them, is also profound. We're part of the universe, made of its matter, following its laws. Yet we can step back and study those very laws, formulate theories about them, test predictions, uncover deeper patterns. This reflexive capacity, where the universe becomes aware of itself through us, is remarkable. We're the means by which the cosmos contemplates its own nature. This suggests that consciousness and intelligence might be built into the fabric of reality in some deep way. Not that the universe is itself conscious, but that conscious understanding is a natural outgrowth of its lawful structure. The same laws that govern atoms and stars also permit the organization of matter into brains, and those brains can discover those laws. There's a kind of coherence, a self-consistency to this that feels significant. Some see purpose or teleology in this. Perhaps the universe is structured to produce observers, to give rise to beings who can understand and appreciate it. Perhaps consciousness is not an accident but a goal, written into the laws from the beginning. This is speculative, of course, and many scientists resist such teleological interpretations, but the fact remains: we're here, we are conscious, we can understand the laws, and that seems like more than mere coincidence. Whether or not there's cosmic purpose, we can create our own purposes within the framework the laws provide. We can choose to investigate nature, to create beauty, to reduce suffering, to explore space, to tell stories, to build communities. The laws constrain our choices but don't determine our values. We make meaning in a lawful universe, not despite its lawfulness but within and through it. As you lie here pondering these mysteries, consider your own place in this grand scheme. You are stardust, atoms forged in ancient supernovae, now arranged in a pattern that thinks and feels and wonders. You are subject to the same fundamental forces and quantum rules that govern everything else, yet you have emerged as something unique, a conscious observer contemplating the cosmos that created you. The laws that made you possible also make your thoughts possible, your dreams, your capacity to love and create and question. When you wonder why there are laws, you're exercising abilities that the laws themselves made possible. There's something beautiful in that circularity, that self-reference. The universe following laws has produced creatures who can discover and question those laws. Perhaps that's part of the answer to our question. The universe has laws because lawful universes can give rise to order, complexity, life, and consciousness. In chaotic universes, nothing interesting happens. In lawful ones, galaxies form, stars ignite, planets coalesce, life evolves, minds emerge. We exist to ask the question because the answer includes the possibility of questioners. This doesn't fully explain why our particular laws exist rather than others. It doesn't explain why there's something rather than nothing. These deep mysteries remain. But it connects our existence to the lawfulness of the cosmos in an intimate way. We are not separate from the universe asking, about it from outside. We are part of it, expressions of it, the means by which it knows itself. So as you drift towards sleep, hold this thought. You are the universe experiencing itself, understanding itself, marveling at itself. The same forces that created galaxies created you. The same laws that govern the quantum vacuum govern your neural impulses. You are continuous with everything, part of one vast interconnected lawful whole. And in the morning, when you wake, those laws will still hold. Gravity will keep you grounded. Electromagnetic forces will hold your atoms together. The nuclear forces will power the sun. The quantum rules will determine how particles behave. The universe will continue its lawful dance and you'll continue to participate in it. Conscious, questioning, wondering. That's enough. That's more than enough. Sleep now, part of the cosmos, embraced by its laws, sheltered by its patterns. Good night.